Last talk of the session is going to be by Leo Singer, who's going to talk to us about UVEX.
Hi. So this is a little bit of a change of pace because rather than talking about ultra-relativistic transients themselves, I'm going to talk about how we actually go about scheduling one of these surveys. And so this is a bit of more of a nuts and bolts talk. So it's my responsibility as part of the UVEX team to deliver the ground software that arranges all of the different surveys that we're going to be doing kind of at the same time with different cadences and with different depths, along with community ToOs. So it's my job to shepherd and to carefully spend that most precious resource, which is time on orbit. And because of that, my title within the mission is Time Lord. So for the remainder of this mission, I will thank you to address me by the traditional title of a Time Lord, which is Your Lordship. So quick outline here. I'm going to talk a little bit about the mission itself, the main science that we want to do, and sort of what the different modes of observation modes are. I'm going to talk about the all-sky survey strategy, and I'm going to talk about the electromagnetic gravitational wave follow-up strategy. So UVEX is NASA's next mid-range Explorer mission. It's scheduled to launch in 2030. So it's very complementary to Ultrasat in a lot of ways. It has a much smaller field of view. So it's only about 10 square degrees, but it's much more sensitive and it has a much smaller PSF. Actually, the PSF is by design really well matched to ground-based follow-up. And we observe simultaneously in a near UV and a far UV filter. And we also have a long slit spectrograph. So we're going to perform this deep cadenced all sky time domain survey in these two bands with high image quality. And we're also going to perform targets of opportunity for gravitational wave and also other multi-messenger events. And we're also going to execute ToOs submitted by the community. So UVEX has three main science pillars. We have the low mass, low metallicity galaxy frontier. And so there we're going to go out and find low redshift, low metallicity galaxies, and we're going to use them to diagnose their cosmic ecosystems. We're going to do follow-up of multi-messenger and time domain sources. So those include gravitational wave mergers, shock breakout, core collapse supernovae, tidal disruption events, all of the same things that we've been hearing about throughout this session. But UVEX is also going to leave behind this really one-of-a-kind all-sky ultraviolet survey that's going to be 100 times more sensitive than GALEX, and it's going to cover the entire sky, whereas GALEX kind of had a lot of sort of holes in it here and there. So it's going to leave behind this all-sky survey that is comparable in depth to Rubin, but at much shorter wavelengths. So we have three key instrumental capabilities. We have this wide field imager that, again, we have both a near UV and a far UV filter. We have high angular resolution across this very large field of view. And we also are able to do broadband UV spectroscopy, which we expect will be the main mode that people are asking for in community ToOs. So in terms of imaging, we have several surveys that are going on all at once. We have the all sky survey, which is literally 4 pi. And we have cadences that are distributed over 1 day to 4 months. Obviously not the entire sky is imaged at a cadence of 1 day, but portions of it are. We have the LMLZ imaging survey, which has an area of about 7,500 square degrees, which we go to a depth that's equivalent to about 5 normal survey visits. And we have an area of 500 square degrees, which overlaps with the cosmos field, which we're covering to a depth that's equivalent to about 50 visits. We're doing an imaging survey of the Magellanic Clouds that we're going to hit twice per week. And then we have, within the survey, we also have spectroscopic targets, which include some of those low mass, low redshift galaxies that we'll be finding, and also strip stars in the Magellanic Clouds. We have ToOs that our team is going to be triggering, which include imaging for those gravitational wave error regions and early time spectroscopy for core collapse supernovae. And lastly, we have community ToOs. So, so this is a lot of things to manage. And so the first step is to divide and conquer. So UVEX, first of all, has a scheduled ground contact every 6 hours. So we call each of those 6-hour blocks a scheduling block. We can image between 19 and 20 fields per block. So for simplicity, what we're going to do is we're going to break up the entire sky into prearranged sequences of 19 to 20 fields that we always visit all at the same time. And then for spectroscopy, we're going to, for each survey block is just going to be, that's assigned to spectroscopy will be all spectroscopy. And then lastly, the gravitational wave, for the gravitational wave ToOs, that's an imaging focused mode, but that is more specialized than the survey imaging mode and has fully adjustable exposure times. And lastly, there's going to be an Uber scheduler, which just decides for each block which of these three modes we're operating in. Okay, so now let's talk about how we build up the sky grid. So first off, because we're observing in space, and because we have solar panels that we always want to keep oriented toward the sun, that means that whatever point on the sky that we want to look at, there is a unique roll angle up to rotations of 90 degrees that of the field of view that allows us to maximize the amount of solar illumination. Because we want to have reference images that completely cover the entire sky without gaps, that means that when we decide how close together the fields need to be, we need to think about not the square footprint of the camera itself, but the circle that's inscribed within it. And so this is a particular patch of sky and shows how those fields shift as a function of time throughout the year. So about half of the sky will be covered by a single field, and about 40% of the sky will be will have over a little bit of overlap. But that's the price you pay to cover the entire sky. So the survey grid is just a geodesic polyhedron, called the vertices of a geodesic polyhedron. And this covers the entire sky with as few as possible of these circles. So next, we have to think about how deep we need to go for each of these regions on the sky. So this is a map of all of the different survey regions. So we have the low mass, low redshift wide footprint, which interestingly includes the United States. And then we have the LMLZ deep fields, which include the Cosmos field, which is that hashed region there, and then a few isolated fields that really are each just a single image. And then we have the Magellanic Clouds. So now we take that grid that I showed you, and we assign a weight to each point. And so that weight is proportional to the number of times throughout the entire survey that we have to visit it. Then we partition that grid into blocks that are contiguous, so that whenever we go from a ground contact to doing imaging, we visit a whole bunch of contiguous fields, and then we come back to where we started and then slew back to the ground contact. And so these blocks can have non-uniform shapes to conform to the regions that we are interested in looking at. And so this is the first, how many days? This is the first 102 days of the mission. And yeah, can I get an ooh, ah, ooh? Thank you. That was very satisfying. Right. So I'm working right now on integrating the other surveys into this and expanding this to cover the full 2 years of the prime mission. So I only have a few minutes left before we go to questions. And so I just wanted to switch gears and talk about the EMGW strategy, which is actually way, way more mature because it has a lot of heritage from Dorado, which is a small sat UV mission that was a concept that I worked on before we started UVEX. And I just wanted to point out that the rest of this work involves a lot of contributions from 3 early career researchers: Sidney Leggio, who's a grad student at USC, Alexander Criswell, who's a postdoctoral fellow at Vanderbilt and Fisk, and Weitzman Kendrabogo, who's a graduate student at the Observatoire de la Côte d'Azur. So like I said, the gravitational wave follow-up is a bit of a special case. We have all of the constraints on the field of regard, and we also have a gravitational wave localization map, which is a 3-dimensional distribution in right ascension and declination and distance. And we also have a, I call it a luminosity function, but we have a guess about how bright kilonovae should be. And so we take all of those things, and for each pointing, really for each point on the sky, we know what the backgrounds are, and so we can predict for each point how deep we would have to integrate in order to detect a kilonova of a certain brightness. And then we know that whatever exposure time that we actually pick for a given field, only the pixels for which that limit is less than the exposure time that we use actually count. So we do all of those things, and the exposure time can be different for each field. And oops, that was supposed to be a backup slide. Okay, so the strategy about how we actually decide which fields to follow up is really simple. We just run the scheduler for each event. The scheduler predicts what is the probability that we're going to detect the kilonova, and we just trigger if that probability exceeds a given threshold. So I see I'm out of time, so I'm going to stop there. I do have some questions written down responding to what Ryan put for prompts for the topic of the conference, but yeah, I'll take questions first.
All right. Thanks, Leo, for the awesome talk. Questions for our Time Lord? Okay.
Thank you. That was really cool. My question is, it's a 2-year mission. What happens after 2 years?
Well, it's just like any other NASA mission. We put in, we'll start having annual senior reviews. We have to show that we're still doing awesome science and that they should still pay us, and they should still keep the lights on at the science and mission operation centers. But UVEX is in a really high orbit. It's never going to re-enter. So it doesn't have any, well, it has consumables, it has fuel, which we will use very, very slowly to dump momentum, angular momentum that accumulates. But yeah, there's no, that's just the funding that we're asking for is the 2-year prime mission.
Okay, cool. Thanks.
Hey, Leo, nice talk. Can you tell us a little bit more about the community TOO program and what might be possible?
Not too much, because that's Subi Ghazari's department. Yeah, I'm sorry. So we're working that out, but when we get closer to launch, we'll have community workshops. But I mean, I think the goal is, the mission is designed to be able to do TOOs with really, really rapid turnaround. So I think our vision is that it's a lot more like Swift and a lot less like Hubble.
All right, last question from Eric.
Hi, Leo. Great talk. You are trying to schedule lots of different observation modes that are sort of not really comparable.
Correct.
Is there how is the Uber scheduler going to think about what its success criteria is?
Well, that's a good question. But so I kind of was vague about that because I haven't figured out that yet, but I mean, the basic approach is just like a multi-armed bandit might do the trick. So, yeah. Uh-oh.
Super quick.
Follow-up question?
Super quick follow-up.
You had cadences that had a huge range from
Yeah.
like as scientists, how should we think about what type of cadence we'll get? Is it TBD and you're looking for input, or is it certain fields have super high cadence versus low cadence?
Yeah, no, I have a little bit of an answer to that on one of my slides. So the very maximum cadence is 3 months because we have a sun avoidance angle of 45 degrees. And so we have to wait a quarter of a year for the sun to move out the way. That's some, I mean, we're working on doing cadence simulations, and we're going to be, well, at least within the team, we're going to be producing different, looking at different ways of partitioning which parts of the sky we're going to visit with different cadences. And yeah,
All right, let's thank Leo again.